Morning, students. Myself, Vijay Shankar from Electronics and Communication Engineering Department, Chevrolet Engineering College in Chevrolet. Today, we are going to discuss about the sampling examples. So, before going to do some more examples of the sampling, I have to what we discussed previously. The first one is sampling and sampling theorem, and the reconstruction of the signal and the sampling techniques, the three types of techniques: instantaneous sampling and natural sampling and flat top sampling. Okay, and some more examples you have to go for discuss today's class. And also we already discussed about the aliasing effect. The Fs is greater less than or equal to 2Fm. Now you can see some more examples in the sampling. That is, EFS is less than or equal to 2Fm. I already say that aliasing effect. That aliasing effect can avoid by using the EFS is greater than or equal to 2Fm. The greater than 2Fm recover the original signal. And see now, before going to that, you can explain about the block diagram. The first block is a sampler, and with the input, analog input, and the second block, the analog input output sampler is a discrete time, a continuous amplitude, discrete time signal, and it is a continuous amplitude. And second block is a quantizer. And it is also the discrete time signal. It is also the discrete time signal, but it is a discrete amplitude. Okay, my dear students. The first one is a continuous amplitude with a discrete time signal, and it is also the discrete time signal, but the input of that is a discrete time signal, and output is also the discrete time signal with a discrete amplitude. Then after that, it is given to the signal is given to the encoder. The given signal is given to the encoder. The output is a digital signal with the zeros and ones. Okay, my dear students. Analog input is given to the sampler, and sampler performs the operation on the input signal. It gives a discrete time signal with a continuous amplitude. The characteristic shows that the amplitude is continuous and the time is discrete. So continuous amplitude, and in the quantizer, after the quantizer, we'll get the discrete time signal with a discrete amplitude. Now you can see the amplitude is also the discrete here. Amplitude is a discrete, and the time is also discrete. The slowly it is increases and decreases according to the waveform. Okay, my dear students. The output of the discrete quantizer output. An encoder is a digital signal, zeros and ones. My dear students. Okay. Now, go for take some more examples in the sampling by using the Fs is greater than or equal to, or the Fs is equal to greater than or equal to 2Fm. Greater than or equal to 2Fm, and greater than the 2Fm is a oversampling, and equal to the 2Fm is a sampling, and less than 2Fm undersampling. The less than 2Fm called as undersampling. Okay, the Fs is less than the 2Fm undersampling. call it as a aliasing. The effect is aliasing effect. That effect we are calling it as a aliasing effect. It means higher frequency is in the lower frequency and the lower frequency is in the higher frequency. There is overlapping occurs in the aliasing. That aliasing is avoided by the greater than 2FM and is equal to the 2FM. Greater than the 2FM is a over sampling. In that we'll get the God band and is equal to 2FM. See, by using the low pass filter, the practical low pass filter, you can recover in the greater than the 2FM. FS is sampling frequency. And the sampling frequency is equal to 2FM. It is a sampling by using ideal low pass filter. By using the ideal low pass filter to recover the original signal. Okay, my dear friends. Now, there is three types of techniques we already discussed about in the sampling. The first one is instantaneous impulse sampling. And second one is a natural sampling by using the chopper circuit or the chopper sampling here. And the third one you can see, that is a flat top sampling. By using the sample and hold circuit. We are using here the sample and hold circuit. Here also it is a chopper. Nothing but the chopper sampling, the chopper circuit we are using. And in the instantaneous impulse sampling is there is no any practical. It is not useful in the practical values. Okay, and the maximum interference, the noise is maximum there, and in the natural sampling, the minimum interference, and the flat top sampling also the minimum interference, nothing but the noise. Okay. Now we go for the next one. We already discussed about all the sampling frequencies and the sampling techniques. Okay. Some of the examples we can see some of the examples in the sampling that is EFS is equal to the 2 into the maximum. FS is equal to 2 into the maximum frequency component. FS is equal to maximum frequency component of a signal X of t. Okay, the maximum frequency component present in the signal X of t, that is X of t is equal to, if having the X1 of t one signal plus the X2 of t is another signal and so on, the Xn of t the signal, the sampling frequency Fs is a 2 into the maximum frequency component present in the signal X of t. Okay, the maximum frequency component present in the X of t signal. Okay, my dear students. It having the two signals, if I am assuming X1 and X2, whichever the maximum, you can multiply with the 2 to get the frequency. Now the X of t is equal to X1 of t plus, if the X2 of t is a product we have, the sampling frequency Fs is equal to 2 into sum of the frequencies of F1 and F2 and so on the Fn. If it is a product of the signals, the time domain, the product of the signals X1 and X2, if the plus values, the 2 into maximum frequency component present in the signal, and whenever if it is a product, the frequency sampling is a 2 into the sum of the frequency components. And suppose if it is X of t is equal to x of t is equal to x1 of t with the convolution of the x2 of t, the time domain, my dear students. Listen carefully here. Time domain signals. What is the sampling frequency now? The fs is equal to 2 into the minimum of the frequency components. The minimum of the frequency components, what we are giving in the time domain function. F1, F2, and so on, Fn. 2 into minimum of the frequency components. For the x of t signal, the convolution is given the two signals. Okay, the plus values are the two signals, and the another one is a product. So the natural, the n, not the natural, it is a fundamental frequency. The n is equal to the 2 pi by the omega, when the x of n is equal to x of t, where the t is, the x of n is a discrete and the t is a continuous. T is equal to n into ts. N into ts. Okay, my dear students. Okay, this you have to remember these all the things to solve some more examples in the sampling. So let us take the one example. Example is the first example. The given data is the given data of the frequencies. The first one, the x1 of t is equal, is a frequency, the 2 kilohertz, and the x2 of t, the frequency is 3 kilohertz. 3 kilohertz. Now, these are the frequencies, my dear students, maximum frequencies only, maximum frequency. The first one, by using this data, x1 of t, the x1 of t, the Fourier transform, the x1 of t, the Fourier transform is x1 of f, and for that, the maximum frequency fm is 2 kilohertz, is equal to the 2 kilohertz is given. And for the second one, x2 of t, the Fourier transformation, x2 of f, the maximum frequency fm is equal to 3 kilohertz. Maximum frequency fm is equal to 3 kilohertz. Okay, my dear students. Now, to find the sampling frequency of the signals individually, x1 of t, the 2 kilohertz, fm is equal to 2 kilohertz for the x1 of t of the signal, and the sampling frequency fs is 2 fm, the individually, that is equal to 2 into 2 kilohertz. 2 into 2 kilohertz is 4 kilohertz, my dear students. That is individually you can find out the sampling frequency of the x1 of t signal. Okay, the single tone, we can call it as a single tone. I'm not using that as a combining of the two functions. The second one, the sampling frequency fs is equal to 2 fm, it is 2 into 3, 6 kilohertz. It is 6 kilohertz, my dear students. Okay. x1 of t and the x2 of t is given the frequencies. The single tone, you can find the individual frequency components. For the second one, you can see the x of t is equal to x1 of t plus x2 of t. X of t is equal to x1 of t plus x2 of t. Now I'm adding the two functions. Previously, it is individual functions, so 2 kilohertz and 3 kilohertz. Now we can add the two functions to find the sampling frequency of the x of t. See, we already know that the fs is equal to 2 into maximum frequency component present in the signal x of t, when the x of t is x1 of t plus x2 of t, x1 of t plus x2 of t. Okay, x1 having the 2 kilohertz and x2 having the 3 kilohertz. Okay, that is a combination of the two functions. Now, you can see here, the fs is equal to the combination of the x1 and the x2. Now, suppose if I am taking the x1, the band limited to the signal to the -2 to the 2. -2 to the 2 of x1 of f. For the second one, you can see the 3 kilohertz is band limited. So -3 to the 3, -3 in the left hand side, and the right hand side is a +3. See, +3. Now, that is a x2 of f, my dear student. This is the maximum. So fs is equal to, for the x of t, the sampling frequency. For the x of t, the sampling frequency. The x of f, the fs is equal to 2fm. And for the x of t, x1 of t plus x2 of t, the sampling frequency of x of t is equal to 2 into the maximum in both the f of fm is equal to 2 kilohertz and 3 kilohertz. So now we can take the 3 kilohertz on is equal to fs is equal to 6 kilohertz, the maximum frequency in the individual. For the x of t, when the two signals are combined, the x1 of t and x2 of t. Okay, my dear students, the sampling frequency fs. For the second example, if we go with the same data only, my dear students, example, the x1 of t or the x1 of 2t. x1 of 2t, we already know there is a sampling or the time scaling, my dear students, time scaling. Okay, x1 of 2t, the 2 kilohertz, and x2 of t is a 3 kilohertz. With the same data, we did the first one individually, and the second one, we can take this as a second one. X of t is equal to x1 plus x2 of t. Now it is a third one with the same data, my dear students. x1 of 2t, what is the sampling frequency? Okay, what is the sampling frequency? fs. The x1 of t, the Fourier transformation is x1 of f. And that frequency, the maximum frequency fm is equal to 2 kilohertz, and the same, the individually, if I am taking the fm is equal to the 2 kilohertz. So on the signal x1 of t, suppose if the given signal, the x1 of 2t is a time scaling, the Fourier transformation, that is a x1 of a into t, my dear students, a into t, the time scaling. For that, the Fourier transformation you can apply for the time scaling 1 by a, nothing but here the 2, x of x1 of f by the 2. According to our time scaling property, x of at, the Fourier transformation is 1 by the magnitude of a, and x of f, or the omega, actually, the omega by the a. Okay, my dear students, omega is angular frequency. Okay, the a value is a 2 here, and I written is a f instead of omega as a 2 by f. The short code notation is a f, and the a value is a 2. Okay, my dear students, it is the x1 of 2t, the Fourier transformation. x1 of 2t, the Fourier transformation is 1 by 2, x1 of f by 2, where a is the 2. Now the x1 of 2t is a compressed signal. We already discussed about this one, my dear students. x1 of 2t, the compressed by the factor the 2, the time domain signal. But in the coming to the frequency domain signal, the x1 of f by 2, because it is a divided here, it is expansion or expanded by the factor or by the sample, the same factor of that is a 2. Expand by the same factor, that is a 2, or by the factor the 2. Okay, my dear students. So the fs of x1 of 2t is 2 into. Now we are finding out of the x1 of f by 2. x1 of f by 2 for the frequency. What is the frequency here? The fm is equal to 2 kilohertz for the x1 of f. Now the value is increases because it is expanded. It is increases. fm is equal to 4 kilohertz because it's the frequency is a by 2. the 4 kilohertz. Okay, my dear students, it is a very important 4 kilohertz. The sampling frequency f and the sampling frequency f by 2. So 2 kilohertz, f by 2 is a 4 kilohertz. Okay, 4 kilohertz for the maximum frequency, because it is a 1 by 2 is multiplied in the frequency. Multiplied in the frequency, my dear students. So fs is equal to 2 into the fm, that is 4 kilohertz, that is equal to fm only. The fm what we are taking is already for the x1 of f by 2, because it is expanded. Already the fm is equal to 2 kilohertz, and now it is a 8 kilohertz will get. Fs is equal to 8 kilohertz for the sampling frequency of x1 of 2t. For the sampling frequency of x1 of 2t, my dear students. When it considers x1 of t, the maximum frequency is 2 kilohertz. When it considers of x1 of 2t, the maximum frequency is 4 kilohertz. So what is the final, the sampling frequency? The 2 into 4 kilohertz is equal to 2 into 4 kilohertz is equal to 8 kilohertz, my dear students. By using the time scaling property. By using the time scaling property, if A is multiplied, it is a compressed. If A is divided, it is a expanded. Okay, divided 1 by 2. Okay, my dear students. Divided, the 4 kilohertz is increases. So Fs is equal to the 2 into 4 kilohertz is a 8 kilohertz is a sampling frequency. 8 kilohertz is sampling frequency of x1 of 2t. x1 of 2t function. Okay, my dear students. 1 by 2, the x1 of f. x1 of f by 2. Another example, it is a fourth example. If we go, x2 of t is equal x2 of t minus 3. x2 of t minus 3 is a x2 of t. The Fourier transformation is a x2 of f, x2 of f, and that frequency, the fm, already we given the first data, that 3 kilohertz. It is a 3 kilohertz. And now the x2 of t minus 3, the Fourier transformation. The 3 samples is shifted towards the right side because it is a delay function. The Fourier transformation is multiplied with one of the property we are know, the x of t minus t naught is the Fourier transformation is t minus t naught Fourier transformation is e power minus j. Actually, it is a omega into t naught. T naught is a sample. So x of omega. And similar way, the Fourier transformation, e power minus omega is a 2 pi f into t naught. That the shortcut notation, if it is t naught, you can write there into the x of f actually. The 2 pi f all, otherwise it's a 2 pi f. After that, you can write the shortcut notation. The Fourier transformation is e power minus j 2 pi f t naught into x of f. X of f only, my dear students. Okay. Now you can see instead of the t naught, here the 3 is there. The Fourier transformation. The shifting operation you can apply e power minus j 2 pi f, and the t naught is here the 3 x of f, or nothing but is a x2 of f here. X2 of f, because it's a 2 we are taking, so x2 of f, the Fourier transformation. Okay, now the Fourier transformation is e power minus 6 j into something, j into 6 pi f x2 of f. Okay, my dear. Now you can find out the Fourier sampling frequency for the x2 of f1. x2 of f, the maximum frequency is a 3 kilohertz. The maximum frequency fm, the 3 kilohertz. even if it is multiplied with the exponential value also, for x2 of t minus 3, the sampling frequency is, even it is multiplied with the e power minus j6 by f, the x2 of f having the maximum frequency is 3 kilohertz. Nothing but it's a band limited to the 3 kilohertz, my dear students. Okay, for the x2 of f only. Now, the same kilohertz. Now you can find the sampling frequency fs is equal to 2 into 3 kilohertz. That is a 3 kilohertz. That is equal to 6 kilohertz. Okay, even if it is shifted with the samples of the 3 also. Okay, x2 of t, maximum frequency is 3 kilohertz. Maximum frequency is the 3 kilohertz. x2 of t minus 3, the maximum frequency is also the 3 kilohertz on. So the sampling frequency is 6 kilohertz. Okay, it is a band limited to the 3 kilohertz, my dear students. Band limited to the 3 kilohertz. And the sampling frequency is 2 into 3 kilohertz, that is fs is equal to 6 kilohertz. Okay, my dear students. It is a fourth one. We already seen the first, second, and the third. Now it is a fourth one. fs is equal to. Now we go for the fifth one, my dear students. It is not the fourth. Okay, the x of t is equal to x1 of t and x2 of t, the product, or the thing what is a multiplication, or you can call it as a modulation. X of t having the signal x1 of t and x2 of t. X of t is the Fourier transformation. X of t, the Fourier transformation. X of f, let us take it as a x1. X1, the x1 of f. Similarly, the x2 of t, the Fourier transformation. Fourier transformation x2 of f. The Fourier transformation is x2 of f. The total x of t, the Fourier is equal to the x1 of t and the x2 of t. What is the Fourier transformation when the time is product? The time is product means the frequency is a convolution. Frequency is convolution. x1 of f convolute with the x2 of f. Convolute with the x2 of f. Okay, my dear students. That is equal to x of f. That is equal to x of f. Now you can find the sampling frequency of x of f. It is a x1 of t. The x1 of f is a 2 kilohertz, and for the x2 of f is a 3 kilohertz. 3 kilohertz. I can find out for the frequency of x of f by combining the two functions x1 of t and x2 of t. Okay. Now the fs, the sampling frequency fs, the 2 into because it is a product x1 of t and the x2 of t. We already know the formulas are there. The 2 kilohertz and the 3 kilohertz is a sum of the frequencies, the sum of the frequencies of the x1 of f and the x2 of f. That is a 2 plus 3. The f1 is a 2 and f2 is the 3. The 2 into the sum of the 2 into the sum of the 5 is equal to 10 kilohertz, my dear students. 10 kilohertz, the sampling frequency. Okay, for the x of t, having the product is the x1 of t and the x2 of t. If it is an addition, we'll get it is a maximum of the frequency component. But it is a product means the sum of the product frequency components. Okay, you see here, first one, the x1 of t and the x2 of t, plus means whatever the maximum signal we can take, that you can multiply to the 2 to get the sampling frequency for x of t. Okay, my dear students. Now, it is a product x1 of t and the x2 of t. x1 of t and x2 of t. Product means the sum of the sampling frequency of the x of t is a 2 into the sum of the sampling frequencies are 2 and F1 and the F2. Let us take it is F1 and F2. The 2 kilohertz is for 1 and the F2 is a 3 kilohertz. The 2 into 5 is a 10 kilohertz. 2 into 5, the 10 kilohertz, my dear students. Okay. That is the fifth one. The product of the two signals is given, x1 of t and x2 of t. Now you can take the another example is a fifth. Let the x of t is equal to x of t with the convolution of x1 of t with the convolution of x2 of t, x1 of t with the convolution of x2 of t. Okay. Convolution. Convolution means that the time domain is a convolution. The x1 of t, the Fourier transformation is x1 of f. The frequency, the maximum frequency is 2 kilohertz is given. 2 kilohertz is given. And x2 of t, the Fourier transformation, x2 of t, the Fourier transformation is x2 of f. The maximum frequency, the 3 kilohertz is given. 3 kilohertz is given. Now, take the x of t, having the signals x1 of t with the convolution of x2 of t. The Fourier transformation is, the time domain is a convolution in time. Convolution in time, my dear students. We already know the property, one of the property. Convolution in time means product in the frequency. And here the product in the frequency, the time means we got it here. Convolution in the frequency. Product in the time, convolution in the frequency. Now here the convolution in the time, product in the frequency. The convolution in time, the product, the x of f is equal to x1 of f into x2 of f. Into x2 of f. Okay, my dear student. To find the sampling frequency of the x of t, that is a 2 into minimum of the two frequencies. Minimum of the frequencies x1 of t and the frequency of x2 of t, because it's a convolution, f1 and f2. What is the minimum? Which is the minimum here? The f1 and f2. F1 is a 2 kilohertz and the f2 is a 3. Okay, my dear students. F1 is a 2 and f is a 3. 2 into 2 kilohertz, because the 2 is a minimum. 4 kilohertz will get for the sampling frequency of x of t. The signal is in the convolution, the time domain. Time domain is a convolution. The 2 into minimum of the frequencies f1 and f2. In that, the minimum frequency is a 2. So you can multiply with the 2 with the 2 kilohertz. You'll get the 4 kilohertz, my dear student. The sampling frequency for the given x of t signal. X of t signal. And here, the sum of the two frequencies. 2 into the sum of the frequencies. Because the time domain is a product. Sum of the frequencies is 5 here. And here the convolution is given. So it is a minimum of the two frequencies. Take only the minimum. Which is the minimum? That only, the FM. That is x1 of t and x2 of t. F1 and f2, that is a 2 and the 3. To get the 2 into 2 kilohertz is 4 kilohertz. Okay, my dear students. It's a very important how we can find the next example. If you go the next example, that is x of t is equal to sinc function or the sine 2 pi into 10t. 2 pi into 10t. Sine function, my dear student, not the sinc here. Sine function. Sine 2 pi, the 10 is nothing but is a fm, my dear students. You can comparing this function with the sine omega t. Sine omega t. The sine omega you can write as a 2 pi f m. Take the fm. Fm. Now the 2 pi into the 10 it is. Fm is nothing but it is a 10 into t. 10 into t. What is the maximum frequency for the sine function given? The 10 hertz only. Don't write it as a kilohertz, my dear students. 10 hertz for the x of t signal. Now the sampling frequency for the given signal, the 2 FM, the 2 into 10 kilohertz, not the kilo, it is only 20 hertz. 20 hertz. Fs is equal to. It is a single tone. Because it is a single tone, it having only the one signal, that is a sinusoidal signal. FM is equal to the 10 kilohertz when comparing with the given function with the sine omega t. You can represent the omega as a 2 pi FM. The FM is 10 hertz is given. So Fs is equal to 20 hertz for the sine function. Okay, my dear students. FM is equal to 10 kilohertz. And it is a single tone signal. Fs is equal to 2 FM is a formula. The 2 into 10 hertz, you get the Fs is equal to 20 hertz. Fs is equal to 20 hertz. Okay, my dear students. Coming to the next example. X of t is equal to cos 2 pi 20 into t minus sine 2 pi into 50 into t. Okay, my dear students. X of t is equal to. It is a multi-tone. X of t is a multi-tone cos function and the sine function. The cos omega t plus minus sine omega. So cos omega t minus sine omega t. Okay, my dear students. Now, first one is omega 1, you can assume omega 2, and the cos 2 pi f1 into t minus sine 2 pi f2 into t. f1 is a 20 hertz and f2 is a 50 hertz. f2 is a 50 hertz. Now it is a multi-tone. The combination of the Fs is equal to 2 into maximum frequency component. Maximum frequency component in the signal x of t. F2 is a maximum. So you can take the 2 into 50 hertz is equal to 100 hertz. 100 hertz. For the single tone, it is a multi-tone signal, combination of the cosine and the sine functions, my dear students. For each single tone means F1 is equal to 20 kilohertz, 20 hertz, and F2 is a 50 hertz. But here it is a combination of the two signals. Take the which is a maximum frequency component in that signal. Another example, if you go, example x of t is equal to sinc t. Sinc t. We know the sinc t or the sinc theta is equal to sine pi theta by the pi theta. Sine pi theta by pi theta. Sin theta we already know. Now we can write in the t function the sine pi t by pi t. Sine pi t by pi t. Okay, my dear students. Then convert that into the function. Convert that function is a sine 2 pi fm into t whole divided by 2 fm pi into 2 fm into t, my dear students. Okay. The denominator is the 2 pi into fm and the numerator also the 2 pi 2 fm. To get it is a same function. Now the maximum frequency, the fm is when comparing the value is a 1 by 2. Okay, to get the sine pi t by the pi t in this function. So you can substitute the Fm is equal to 1 by 2. The sine pi t by pi t will get. Fm is equal to 1 by 2 the hertz. Okay. Now the sampling frequency Fs is equal to 2 into Fm. For the sinc function, 2 into Fm, the 2 into 1 by 2, that is equal to 1 hertz. 1 hertz, my dear students. For the sampling frequency of the sinc function, Fs is equal to, okay, sinc theta, sinc pi by theta by pi theta, and it is a sine pi tt by pi t. And you can write the function as a 2 pi Fm into t, and pi by pi into 2 Fm into t. That's frequency component is Fm, and as a sine pi and the pi to get it is the same function, the Fm is equal to, you can keep it as a 1 by 2. Get the sampling frequency x of t. Fs is equal to 2 into Fm, 1 hertz. For the sinc function, sinc t. Okay, my dear students. One kilohertz. Now another example, you can see the example x of t is equal to sinc square of t. Sinc square of the t. That is equal to sinc t ct is equal, sinc t is equal to sine pi t by the pi t, my dear students. So the x of t is equal to sine pi t whole square by the pi t whole square, that is equal to sine square pi t divided by the pi t whole square. We know the trigonometric function, the sine square is a 1 minus my dear students, 1 minus cos 2 theta. 2 into theta is a pi t here. Okay, theta is a pi t, my dear students, because it is a sine square. Theta is a pi t. So cos 2 pi into t divided by pi into t whole square. Pi into t whole square. Okay, for 1 and the cos theta, whatever the given the function, the sinc square. 1 is a maximum frequency. What is the maximum frequency? It is a 0 here, because it is a constant. For the cos 2 pi into t, the maximum frequency Fm is equal to 1, because it's a 2 pi Fm. 2 pi Fm, the omega is equal when comparing 1 hertz. 1 hertz, my dear students. The two functions we have. See, so the Fm is equal to 0 and Fm is equal to 1 hertz. Okay. Now, the sampling frequency of x of t is equal to 1 by the pi t whole square as a one signal minus cos 2 pi t by pi t whole square. The two signals are the multi-tone. The two signals, one by the first one is a frequency is a 0, second one frequency is a 1, maximum frequency. So sampling frequency 2 is equal to 2 into the maximum frequency component, 2 into Fm, that is a 2 into maximum frequency component is a 1 kilohertz, 2 hertz. Okay, my dear students, sinc square t is equal to the sampling frequency is a 2 hertz. Okay. And similarly here they are 1 hertz for the sinc t. 1 hertz is a sinc t. Sinc square t is a 2 hertz. Okay, my dear students. In this we have the another method is also another method to find the sinc square of t. Another method, the second method you can see. It is a method 1, first one. You can take the second method, method 2, the second method, my dear students. Directly we can write it as a sinc square t. The x of t is equal to sinc square as a sinc t into sinc t, the square of the sinc square, now we already know the sinc t, the frequency component, the frequency component, my students, it is a fm is x1 of t. You can assume the second one is x2 of t. That fm of the x1 of t is a 1 hertz. Is fs is equal to 2 into, it is a product now. The product means the sum of the two frequencies. What is the x1 of t? The frequency component is a 1 hertz. Okay, already we've seen the sinc t is equal to, what is the frequency? The 1 by 2, my students, plus, and for the second one, for the second sinc t is equal to, see the maximum frequency component is a 1 by 2, 1 by 2 plus 1 by 2. For the sinc, 1 by 2 plus 1 by 2, the 2 into the sum of that one. 1 by 2 plus 1 by 2 is a 1 hertz, as a 2 hertz. So directly like this is the second method. First method showing directly by using the trigonometric function of c square, sin square theta, sin square pi t, the 1 minus cos 2 theta by the 2 theta. Fm is equal to 0 first term, and second term is Fm is a 1 hertz. Okay. The first one, the sinc t is Fm is equal to 1 by 2 is a maximum frequency. Directly using that, apply here, taking of the two signals as a product, x1 of t and x2 of t. And take the sampling frequency, x1 of t and x2 of t. Sampling frequency is the sum of the frequency is 1 by 2 plus 1 by 2, the 2 into 1, that is a 2 hertz. 2 hertz, my dear students. Okay. Sinc square of t, the sampling frequency is a 2 hertz. We can find out by using the method 1 with the trigonometric function, and method 2 directly by taking off a product. Okay. Now go for the another example. X of t is equal to sinc t with the convolution of the sinc t. Sinc t with the convolution of sinc t. For the sinc t, the maximum frequency is 1 by 2. We already know. The maximum frequency, the fs is equal to 2 into the minimum of the frequency components. What is the minimum of the frequency component? The sinc t, the fm is 1 by 2 hertz, and for the another sinc is a 1 by 2 hertz. Both are, it is a 1 by 2 only. Okay, the minimum is 1 by 2. For this the convolution of the two signals, the minimum is the 1 by 2. So fs is equal to 2 into the minimum is 1 by 2 of f1 of t and f2 of the frequencies. Okay, so 1 by 2 is the minimum. So fs is equal to 2 into 1 by 2 is a 1 hertz. The sinc t with the convolution of sinc t. Okay, my dear students. Sinc t with the convolution of sinc t. The fs is equal to 2 into minimum of f1 and f2. Having the minimum is a 1 by 2 only. Fm, both the functions, 2 into 1 by 2 is a 1 hertz. 1 hertz, my dear students. Okay. So we completed all the functions. The product x1 of t and x2 of t, and addition x1 of t plus x2 of t, and the convolution x1 of t with the convolution of x2 of t, and also the sinusoidal functions. Okay. Now we go for the another one to find fundamental frequencies. Not the fundamental frequencies, my dear students, fundamental period for any given signal. How we can find the fundamental period for every given signal. What is the fundamental period? N is equal to 2 pi by the omega. The 2 pi by the omega. The omega is angular frequency, my dear students. Angular frequency. We already seen all the functions. to find the sampling frequencies, that is addition, product, convolution. And also sinusoidal functions and the cosine functions are combining, and the sinc function and the sinc square t and the sinc t with the convolution of the sinc t functions also. Okay, my dear students, all it is very important. Now go for the another example. Another examples is x of t is equal to sine 2 pi into t. To find the fundamental period, my dear students, 2 pi f into t. You can compare with the sine omega t, sine 2 pi fm into t. What is the fm here now? Fm is a 1 hertz. Fm is a 1 hertz for the given signal. Fm is a 1 hertz. 1 hertz by the students. So the given is a single tone. So the sampling frequency Fs is equal to 2 into Fm as a single tone. You can write as a 2 into 1 as a 2 hertz. Okay. And the t is equal to n into ts, my dear students. When we are converting into the discrete time function as n by the Fs. N, what is the Fs here? The 2. So n by 2. To convert the discrete time function x of n is equal to x of t, where the t and t is equal to minus 1. Now there t is equal to n by n into ts, n by fs. So for the x of n t, now converted to the discrete function x of n. X of t converted to the discrete function x of n, where the t is equal to n into ts. Okay, n by 2. Now we can change x of t signal as x of n is equal to sine 2 pi. What is the t we got here? The t is equal to n by 2, my dear students. T is equal to n by 2 because n into ts we have n by the 2. 2 to get cancelled there. Sine pi n. Sine pi into n. Okay, for the time domain signal, and now there's a frequency domain. It is a continuous. Now the x of n is a discrete. X of t is a continuous, x of n is a discrete function. Sine 2 pi t is a continuous, and the discrete is a sine pi n. X of n is equal to, the variable is n, and there is a variable is a t, my dear students. Variable is n, and the variable is a t. X of n is equal to sine pi n. To find the fundamental period of this function. Fundamental period is a n only. The n means the given function can change. Okay, x of n is equal to sine pi into n, comparing with the sine omega n. Okay, sine omega n, the n is equal to 2 pi by the omega. 2 pi by the omega is a fundamental period for the discrete function x pi sine pi n, for the discrete function sine pi. So the sine pi n is equal to, comparing with the sine omega n, omega you can write it as a sine that is equal to sine omega is a 2 pi f into n. Now the value is here, the f is equal to, the comparing of the functions, pi is equal to, that is equal to sine 2 pi into, the value is f is a 1 by 2 into n, because we got the fm is equal to 1 hertz. 1 by 2. The 2 to get cancelled is a pi n. F is equal to 1 by 2 then. Okay. Or directly you can write it as omega is equal to the pi. Or otherwise directly you can write the omega is equal to pi. The 2 pi by omega has nothing but the pi value. Pi get cancelled, you get the 2. So the fundamental period n is equal to the 2. For the given function x of t is equal to sine 2 pi into t. For the given function x of t, the natural fundamental period n is equal to 2, my dear students. N is equal to 2. Okay. Now, see the characteristics of the sinusoidal function having within the full cycle, how many number of samples per cycle? The 2 samples are there. N is equal to the fundamental period get 2, the number of samples per cycle. The number of samples per cycle is a 2. Okay. Cycle means is a positive cycle and the negative cycle of the sine function. We got the fundamental period is a 2, my dear students. Okay. The given function, the continuous time function converted into the discrete time function, and comparing with the sine omega n, take the omega value and substitute the omega to find the fundamental period n is equal to the 2. Okay, my dear students. N is equal to 2 pi by the pi, that is equal to 2 for the given signal sine 2 pi into t. Another example, we got x of t is equal to sine 2 pi into 100 t. 2 pi into 100 t, my dear students. 100 is a FM here now. So x of t is equal to the given function. The x of t is equal to t, where the t is equal to n into ts, my dear students. When the x of n is equal to, change that it is a discrete from the continuous time function by substituting t is equal to n into ts. Okay, n into ts, nothing but 1 by the fs, and in the frequency components, and the frequency component, and by fs. Fs is equal to, how we can find the fs is equal to, by taking out the fm is equal to, fs is equal to 2 into fm. What is the fm here? 100. For the given time domain function, fs is equal to the 2 into 100 is equal to 200 hertz, is equal to 200 hertz as a given signal of a time domain. Ts is equal to 1 by 200. Ts is equal to 1 by 200 hertz. Okay. The converting of x of n, the discrete time function, substituting the t is equal to n into ts. In that, the ts is x of n is equal to sine 2 pi into 100. 2 pi into 100, you can write as, my dear students, 100 into n. 100 into n by the ts is a 1 by 200. Okay, my dear students. 2 pi into the 100, you can write the fm you already given, 100 into the t. The t now the n into ts, n into 1 by 200. So the fs we got. Okay, my dear students, fs we got the x of n, the discrete function. It is now the t, that the t value. But what is the t value? The 2 pi into 100. The 2 pi into 100. The t value you can substitute as n into ts. Okay, my dear student, that is equal to sine 2 pi into 100 n ts. What is the ts we got? 1 by 200. Ts we got, it is a 1 by 200, my dear students. So substitute that 1 by 200. 1 by 200. Cancel off the 100 and the 2. Denominator 200. That is equal to sine pi n. Sine pi n, my dear students. Now you can find the fundamental period. Fundamental period comparing with the omega. The omega is equal to, what is the omega? The pi on. Because the sine pi n is equal to sine omega n. Omega n. What is the omega here? The omega is equal to pi. The fundamental period n is equal to 2 into pi by the omega is equal to 2 pi by omega is a pi. Pi get cancelled. N is equal to 2. So this function also, the n is equal to 2. The number of samples per cycle is a 2. So the given sinusoidal function 2 pi into 100 into t. Okay, my dear student. This is a way you can find the fundamental period for any given signals, sinusoidal signal or the cosine signal, whatever we have, for the single tone. the singleton functions. X of t is equal to sine 2 pi into 100 into t minus 2. Okay. So with this, we completed all the examples of the sampling and the sampling unit also. We discussed about what is the sampling and what is the sampling techniques or different types of the sampling techniques, and what are the different types of the sampling techniques, instantaneous sampling and some functions, my dear students. You check all these sampling, all the sampling unit, you can write it as a assignment, my dear students. Okay, take that it is an assignment. I already said that you write the assignment for the Fourier series properties and the Fourier transformation properties, and including these also you can write this assignment, my dear students. Okay. We already discussed all the functions. X of t is equal to the product, addition, convolution, sinusoidal function, and the sinc functions, and so on, my dear students. Any doubts, my dear students? Any doubts? Please rise. Okay. Thank you. Thank you, one and all.